In this session, I will introduce different types of neural networks in classifying MNIST handwritten digit images. This should give you ideas to find out what networks you want to study further. First, let's review the building blocks of deep neural networks. Then, I'll introduce you to convolutional neural networks. Next, I'll introduce you to recurrent neural networks. Finally, I'll touch on transformer. When a neural network has two or more hidden layers, we call it a deep neural network. Each hidden layer has an activation function to introduce nonlinearity. The output layer may or may not have activation. We define a loss function based on the task requirement to train neural networks. Mean squared error is for predicting continuous values. Binary cross-entropy is for binary classification. Cross-entropy is for multi-class classification. We also need an optimizer to update network parameters based on the gradients of a loss generated by backpropagation. SGD, Atom, and more optimizers are available in the Torch Optim namespace in PyTorch. Let's look at the implementation of neural networks, starting with a simple neural network with one hidden layer and an output layer. First, it flattens input images of size 28 by 28 to 784. Then, it applies the hidden layer, followed by ReLU nonlinearity. Finally, the output layer applies another linear layer to output losits. The classification accuracy is around 96%. This is a deep neural network since it has two hidden layers. It applies two hidden layers, each followed by ReLU nonlinearity. The classification accuracy is better than the simple neural network. PyTorch is flexible in that we can define a neural network differently. We can combine layers into a sequence of layers using NN sequential. I also specify ReLU as layer, so the forward implementation is simpler. We can also subclass NN sequential and pass all layers in the superinit method. I use the flatten layer, so I don't need to write the forward implementation. PyTorch is very flexible, so you can decide how to combine different layers. In your further study with PyTorch, you'll undoubtedly encounter different implementations of the same neural network. So, get used to these layers and modules. So far, we have used linear layers for hidden layers. Next, let's look at the convolutional layers. When we flatten 2D images into 1D data, we lose the spatial structure of the image. However, a pixel in an image is related to surrounding pixels, forming local features. Therefore, a convolutional kernel uses data from a small area to generate features. For example, a 3x3 area contains normalized pixel values between 0 and 1. We can apply a 3x3 convolution kernel which contains weight values and a bias value. We calculate each pixel value times the corresponding weight value, sum them up, and add a bias value. Let's look at a simple concrete example of a convolution kernel. Suppose we have a white vertical line like this and a kernel to detect such a vertical line. Also, I set the bias to 0 for simplicity. The result of convolution is 3. Suppose we have a white horizontal line like this and apply the same convolution kernel to it. The result of convolution is -1. So, it is less likely a vertical line than in the above case. These kernel weights are adjusted through training, so it's not as simple as this example shows. I hope you understand how a convolution kernel can extract 2D local features. We apply a convolution kernel everywhere in the image as if we are sliding the convolution kernel over the image. Convolution operation supports zero padding. For example, if we have a 5x5 image and apply a 3x3 kernel, the output becomes 3x3. To keep the exact size of 5x5, we can apply zero padding first and then apply the 3x3 kernel. In this case, the output becomes 5x5. So, if we want to keep the size, we can apply zero padding. Convolution operation supports more options like strides and dilation, which I didn't cover. If you pursue studies in this direction, you'll learn how to calculate the number of zero padding required to maintain the input data size, considering all these options. A convolutional layer has multiple convolution kernels to generate features. If we apply 5 different convolution kernels on an image, we can generate 5 output channels. Often, we use max pooling to downsample the spatial dimensions. For example, a 2x2 max pooling with a stride of 2 chooses the maximum value within the 2x2 area and moves to the next location by 2 pixels. So, in this case, the max pooling divides the input data into a set of non-overlapping regions and then takes the maximum value from each region as the output. This retains the most important information from the input data while reducing the size of the data and the number of parameters in the model. We can think of a convolutional neural network having 2 sections of hidden layers. The first section contains the feature extraction layers that use alternating convolutional, activation, and max pooling layers. The second section contains the classification layers using alternating linear and activation layers. Finally, we have an output layer. Let's look at implementing a convolutional neural network to classify the MNIST handwritten digit images. I have organized the feature extracting layers and classification layers using NN sequential. The feature layers contain 2 blocks of 2D convolution, ReLU, and max pooling. Due to the convolution, the number of channels increases from 1 to 16 to 32. Also, due to the effect of convolution and max pooling, the data size changes from 28 by 28 to 13 by 13 to 5 by 5. We flatten 32 by 5 by 5 data for the classification layers. In the forward method, we use the feature extracting layers and classifier layers. The classification accuracy is better than the previous neural networks. So, convolutional neural networks are robust for image classification. They are also used for other vision tasks like object detection and semantic segmentation. There are many well-known CNN models like ResNet, which uses batch normalization and skip connection. Although all these words may not make sense to you, you'll undoubtedly encounter them if you pursue further in this direction. A recurrent neural network, RNN, is an artificial neural network that processes sequential data. It is helpful for modeling time series data, such as stock prices or weather data, because it can retain information about the past and use it to make predictions. The neurons in an RNN are connected in a feedback loop, meaning that the output of a neuron in one layer is fed back into the input of the same layer at the next time step. This allows the network to retain information about the past and use it to inform its predictions. We can use a folded diagram of an RNN to show the overall structure of the network, including the feedback loop that allows the network to retain information about the past. Long short-term memory (LSTM) networks are recurrent neural networks that can capture long-term dependencies in sequential data more effectively than traditional RNNs. LSTM networks have a special neuron called an LSTM cell that can store information for long periods. They also have 3 gates, forget, input, and output gates, that control the flow of information into and out of the LSTM cell. These gates allow the network to selectively retain or forget information in the cell state as it processes the input sequence. In general, LSTM networks can perform better than traditional RNNs on tasks that require the network to retain information about the past for long periods. LSTMs are a powerful tool for working with sequential data on various tasks, including language translation, generation, and speech recognition. Although it is not the most common approach, it is possible to use an LSTM network for image classification. I'm using LSTM as a feature extractor and seeing an image as a sequence of row data. So, an image's sequence length is 28 rows, and each row data contains a vector of 28 values. I set the hidden state size as 784. PyTorch's LSTM, by default, expects input data shape of sequence length, batch size, and input size. I use the permute function to rearrange the input and remove the channel dimension. Then, I pass the last hidden state of the sequence to the classifier. It didn't perform as well as the CNN model, but it outperformed the previous 2 neural networks. So, LSTM extracted some extra features from the sequence image rows to improve the performance. The transformer was introduced in the paper, Attention is All You Need by Vaswani et al. In 2017. It is designed to process sequential data and has achieved state-of-the-art results on natural language processing tasks. One of the critical features of the transformer is its use of the self-attention mechanism, which allows it to focus selectively on different parts of the input sequence and learn dependencies between them more flexibly than traditional recurrent neural networks. BERT and GPT are both models based on transformer architecture. BERT, bidirectional encoder representations from transformers, is a pre-trained language model to understand natural languages. It is trained on a large corpus of unannotated text and can learn the structure and patterns of language by predicting missing words or sentences in the text. GPT, Generative Pre-trained Transformer, is another pre-trained language model specifically designed for language generation tasks. Although the transformer architecture was initially developed for natural language processing tasks, it has also been used in a variety of other applications like computer vision, speech recognition, and recommender systems. Its use is likely to continue to expand in the future. There you have it. I hope you got ideas for studying further and enjoy doing so with PyTorch. Bye for now.